on this computer. Oh, now I'm recording. I apologize for that. So guys, whatever Maxim said, I hope you guys remember it. And if anything, he can repeat it the next lab because I just want to go on. But Maxim, thank you anyways. I'm sorry I didn't record you, Maxim. It would have been nice for you to be on the video. Sorry about that. But you're right. I didn't see the recording up here. I thought I pressed record. Okay, so here we go. Thank you for pointing that out, guys, because we wouldn't have recorded the whole lab. Okay, and okay, and guys, don't send me a chat. I don't have the chats on, so just interrupt, please. I don't feel insulted. I'd rather you guys interrupt and ask me to send me a chat because I don't look at the chats. Okay, so just break in with your voice and say, "Sir, are you recording this?" And then I will say, "No, you're right. I thought I was recording and I wasn't." So I apologize for that. Okay, so now here we go. Okay, so here we go. We're going to be now. So like I said, this is our little project here, typical. You know, these were all the members that we defined last week. And of course, this week we will be designing, basically what we're going to be doing is that we're going to be designing this member here. Then we're going to be designing this member here, and then we're going to be designing that member there. And of course, because of the fact that they're all, excuse me, you know, like they all have equal spans, or all have the same loads, whatever we design these for, it will work for this side. It will also work for that side. So these three members that we're designing here, 1, 2, 3, will be for, this one will be the same as that one will be the same as this one. And then of course, the two lines will be exactly the same. Now, okay, so, okay. Now let me know, guys, I just hope I'm sharing the right screen, because let me know if you see my ADA. If not, I'm probably gonna have to close the screen and open up ADA. So do you guys all see my ADA? Give me a yes or no.
Yes.
Okay, great,
Yes.
great, okay. So basically, okay, so if you guys did this correctly, or if you, okay, so basically here we go. Like if you want, just have a quick overview. I won't go to results right away, just to make sure, okay? Like I said, uh, what I like to do whenever I'm ready to do anything in ADA is I always go to visual graphics, okay, and I always ask for the length of my members. I ask for the shape, and if I want, I can also put the material, but that I can check at the end. And then at the same time, look at the end conditions just to make sure that my geometry is pretty much what I want it to be. So, okay, so basically, okay, I'm sorry, I made it small, but now I asked you to start with a W610 by 25. The reason why I do that is because I tend to take something that's going to be more than what we need. So that therefore, by asking for the self weight, I will make sure that the self weight is a little bit more than what I actually need. And therefore my results are going to be a little bit higher than what I actually need. So that's why I asked you a 125. And if you're not sure, take the heaviest one, take a W1000 and put that in, and that's going to give you the biggest dead load you can ever get. And then when you actually design it, you're going to go and modify it. So here I have 10 meters, 2.5 meters, and so on. So this is what you should be getting. And of course, the end conditions here showing you that this member is pin connected to the two overhangs, okay?
Sir,
And yes,
can you zoom on your support reaction? The one on the left, 1 second.
the
Yeah,
one the one on the left here.
yeah, yeah. Just zoom in.
Okay,
No, just zoom.
you want me to zoom in? Okay.
Oh, so good, so good. Sorry.
Yeah, like guys, the way ADA works, unfortunately, I had an old program where I would actually see a little roller here or a little pin. The way ADA works is that if you still have a red dot in there, that means you haven't released the MZ. If you don't see two yellow lines, then if you see two yellow ones, that means you have a pin reaction. And when you see, this means that you've released it and you only have restrictions in the Y direction. So that's how ADA tells you what kind of support you're actually modeling, okay? So this is a pin. So these are all pins, okay? So that's how you can tell in ADA. Unfortunately, their graphics are not that great. I was surprised because this is a relatively new program, okay? And the graphic, and I bought a program back in 1986, and the graphics, I used to have a nice little pin here, I used to have a nice little roller, just like you saw in your physics book, and I would have a nice little fixed sign, you know, which was very convenient. It was very easy to see. I guess this is a 3D program, and I guess it's harder to do the graphics. I don't know why. Okay, so this is it, okay? And like I said, so this was your structure, and of course, once I checked everything, like once I've checked everything, take off the attributes. And one last thing, okay, just to make sure that everything is good. I don't need the length, I don't need the shapes, just to make sure I assign the right material. Like I said, guys, as long as you assign a steel, you're going to get the same results. The only time that this is going to have a bearing if you, because you know that this program can actually calculate stresses for you. And therefore, if when it comes to the stress calculation, the steel is very important. Otherwise, for the analysis, it won't make much of a difference. Okay, so that's it. And then after that, okay, so, okay, oh, sorry, I wanted to turn that off. Material. Okay. Then of course we had the different load cases. You guys should, like your dead load and so on. And okay, and then your, like pattern 1, pattern 2. Okay, and then if you want, you should never do this all at the same time because it makes absolutely no sense. You don't even know what you're looking at. What this means is this is the self weight of your beam right here, and then this is the dead load, and this is your snow load, and you don't know which load case it is. Anyway, so these are all your loads. Then once you've done in all your loads, you put in all your load combinations, and hopefully, okay, hopefully, let's go back to something a little bit more reasonable. So therefore, then the load combinations, oops, sorry, load combinations, definitions, and of course, I have, for example, 8 of them. I have 4 for strength, and I have 4 for serviceability, and then of course the strength are I multiply the dead load by 1.25, and I multiply the snow pattern by 1.5. That's for strength. And then for serviceability, I just have the snow load multiplied by 1.0. Okay, so I apologize. I told you to put USD here, which is even more accurate. I put LSD. I'm sorry, that's my 70s habit, LSD. But okay. And so that's okay. And then ultimately, because we have different locations and we want to see envelopes, okay, we go and we create an envelope. I create an envelope for strength. For serviceability, it's not that practical. Mind you, it's good, but serviceability, you don't see the values. And of course, under strength, what I do is I combine P1. Here should be USD, 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 USD. I put LSD, I apologize. And so this, it will take all the strengths and put it under one diagram. In other words, we'll take the maximum minimum values and put it right across your sheet. And for
Sir,
serviceability, yes.
continue. I'm sorry. I will when you finish. Sorry.
Okay, so and then for serviceability, I simply take P1, P2, P3, P4. In other words, I just take the snow loads as they are and combine them all into one. Okay, so Omar, go ahead.
Yeah, I'm sorry. There was the green when you went to the like all the loads, all of them. So there
There
was
was a
like
green
a
one.
green.
There was a green
Yeah,
one. Here,
what
yeah,
what's the green one?
that's the self weight of the member.
Oh, so if it doesn't show on mine, what does that mean?
That means you haven't activated the self weight.
Oh, okay. Cool.
So in other words, what you're going to have to do, okay, first of all, did you put it into your calculations, into your load combinations?
I did. I did.
Okay, so the only thing you have to do is you have to go back, pick all your properties here. Okay, so in other words, you're going to have to go back to properties, Omar. You're going to have to pick all your things here, right? You pick them all. I'm sorry, I should have picked members. Okay, picked all your members. Okay, right click on it. You go to properties. And here you're going to have to make sure that you flash out dead load. You understand? You're going to have
Okay.
to make sure that's, if you don't highlight there, the program will not calculate the dead load. If you leave it null, it's going to stay null.
I see. Okay.
So that's where that's the only thing you overlook to do. Okay. Fair enough.
All right.
Now
Thank you.
I hope I didn't screw up my thing. Okay, I'll just, so that's, I'm glad I'm going through this so you guys can see what are the little, let's call it glitches that,
Can I ask a question?
yeah, I just want to make sure, save project. Okay. Yeah, okay, go ahead, Rena. Go ahead. Yeah.
Like, I don't know why in my program, my arrows, like for my supports are going the opposite direction than your arrows. Like I have an arrow pointing up and an arrow pointing to the left. So
You
I
mean like,
think that's true.
but which are you talking about? The first support, the second support, the
All
third,
of them,
the very first one?
all of them.
All of them are pointing the other way?
Yeah, for me.
Well,
Does that matter?
it doesn't matter. It shouldn't have a bearing, but look, I'd have to like, let me go on, Rena, and then like, remember I told you it's very important on how you assign your nodes, your first node, your second node, your third node, and then, so I have no idea why you,
And my dot's still there even though I freed my MC.
what I'm saying is that what you're saying is that if I just go to nodes here, okay, go to structure, go to nodes, what you're telling me is that your yellow arrows are not going up and to the right, they're going down and to the left. Is that it?
No, they're going up and then to the left.
The yellow ones and the right ones are doing the same thing.
Mm-hmm.
Wow. Did you reverse your graphics for some reason?
No, I left it like that, but also like my red dot's still there. So like, even though I released my MC, does that matter?
Well, in other words, you still have a red dot here?
Yeah.
Well, that means that something's absolutely wrong. If you have a red dot here and a red dot there, that means you haven't released your nodes.
But is it just the MC that needs to be free?
MZ.
Oh.
Okay, so in other words, if I come here, okay, and support, this has to be, the MZ has to be free.
Okay, yeah, it's free. I don't know then.
And this is fix.
Mm-hmm.
This doesn't matter. Like I can show you, it won't make a bit, but what's important is that this is fix for the create the pin connection, fix, and then MZ free to rotate about the Z axis. That's all it is, okay? So Rena, I look, if we don't get the same results, what I can do is at the end of the lab, you can share me your file and I can see where you might have, reversed something. But if it doesn't have any, if you get the same results, don't worry about it. You understand? You might have done something to change the graphics. I don't know. Okay.
Thank you.
Okay, so now everything is good. I got my load combination. I got my envelopes. I got my load case. And of course, I want to run some analysis. Okay. And okay. And I close this. And of course, like since I've got an envelope, I'm going to go to envelopes. I'm going to go to strength. Okay. Now, guys, the first thing I like to look at is always my reactions. Okay. And so these are the reactions that I get. Okay. So the first thing I like to look at is my reaction. Now, this is the minimum load. And that's the maximum load. Now, the reason why they do this, and when we get into exterior columns, you can appreciate why it gives you a minimum and a maximum. In other words, this would be load case number 3 when you combine it with your wind, and this would be load case number 4 when you combine it with your wind. So that's very practical. Depending on the situation, you might want to know what the minimum and the maximum is, okay? And these are the maximums and the minimums, okay? So when we get into columns, we're going to come back to this. So in other words, this is the PF that's going down into the column. This is the PF that's going down to, so we're going to take the CF value, or this is CF, we're talking about steel, sorry. In steel, they call it CF. This is our CF value, and therefore we already know what's the resistance the column has to have based on this PF value. So I first thing I look at, and if I end, and this looks pretty much good. And then once I look at my reactions, of course, what I look at, okay, once I look at my reactions, I like to go look at my shears, okay? And I never look at my shear and my moments at the same time, okay? And these are the shears. Now, when you'll see in the PowerPoint, okay, so in other words, this beam here has a maximum shear of 320.9 kilonewtons, okay? And then this is the overhang. So this is the shear for the overhang, or this is the suspended one, and this is the shear for the double cantilever. So when I'm talking about the double cantilever, I'm talking about this. So this is the maximum shear. So that's where I get my shear by VF values for my design. And then ultimately, what I'm really interested in, of course, is my MX values, okay? Okay, so MX. So I apologize, I think I went a little fast, but Nicola, are you there?
Yes, yeah.
Did you activate, so this is to activate your envelope here, you see?
Yeah.
Okay, if you are you getting the same results that I am?
Well, actually, it was slightly different. Like, I think a student said it before, it was like a couple digits off, but other than that, it's more or less the same.
Okay, well, look, if we're in the same ballpark, because what's going to happen is that as we're starting to design it, we're going to have to go replace the members we assume with the real ones, and we have to rerun the analysis. Okay.
Yeah.
So now, guys, if you notice that my moment diagram shows the positive moment at the bottom and the negative moments at the top. If you guys have it the other way around, is that how you have it? If you want to see it like the way that you're always seeing the positive moment like at the bottom and the negative moment at the top, what you do is you simply go to your visual graphics, you go to the very last tab on the visual graphics here, okay, where you go under results, okay, you go under member, okay, bending forces, strong axes, and change the amplification factor to, if it's positive, change it to negative, and it's going to reverse everything the way you normally see it, okay? So that's how you get to change the diagram upside down. I'm just letting you know. If you're otherwise, just leave it the way it is. It makes no difference. So guys, these are the results that we're going to start using to start sizing our Gerber girder. And does anybody else have the same values that I have, or we all have different values? Does anybody have the values that I have?
I
Yes.
do.
Yeah, so far I have the same values as you, but
Great.
can you just go on like one load combination
Go
and
back.
check the moment? Like I just want to make sure I have the same one as you.
Well, if you have the same maximums and minimums here, okay, what we can do is we can go look at the different load combinations. Like for example, that's P1.
P1.
See P1, there's 448 here. Now, if you remember from the lab last week where we said that load combination where we put the 100% in the first span and then 50%, it gives you the biggest positive moment in the first span. Well, that's exactly what this did. It gave me the biggest positive moment that that span will ever have. And of course, remember that when this 100% here and 50% there, that's the same value as what you have on this side. Is that what you get here? 448.02?
Yeah, I get exactly that.
Great. And then after that for P2, is that what you get? And P2 gave you the highest negative moment in the first span and so on. Okay, so this is really, in other words, this is, do you get this? You get 432 up here?
Yeah, I get that too. I don't know
Okay,
why I didn't get it before, but now it's all now I got the same exact
it's all
value.
the same result. So good.
Yeah.
That means Adriano, that means we're either both right or we're both wrong. It doesn't mean that we're both right. Okay, so
Yeah.
keep that in mind. Okay, I don't, but I can, like, in other words, this is for my P3, okay? And of course, if your moments are correct, then your reactions are correct and the shear is correct. You understand? So don't,
Sir?
and then this is P4, okay? So, and guys, like in the PowerPoint, I copy some of this so you'll be able to see them in the PowerPoint if you want to check your results. If you don't have the same results, it can be like you might not have, religiously put them at exactly 2 meters apart and whatever, okay? Or you might have put, you might have made anyways, whatever it is. But if you are in the same ballpark, that's great, understand? That's great. So, and that's it for that. Is there anything else that you guys want me to go over in ADA, or is it pretty much okay? Anton, you have a question?
Yeah, I just want to say I got the same results as you.
Oh, thank you.
Yeah,
Thank
and it's same plus and minus signs.
okay, so in other words,
all
the three of us are either right or we're all wrong, right, Anton? Is that it?
I'm pretty sure we're right.
Make
Oh,
it
thank
four.
you.
Sir?
4 of us. Hey, so far I'm starting to get a little.
We
Anybody
also
else?
have the same, but like, what if it's a decimal off, like
Hmm.
0.03 off? Does that mean that I put something wrong? Or?
No, it could be the program that's rounding up. God, if you're within 0.1 here of this value here, it's the same number. It's the program that can be rounding off. You understand? So don't worry about that. Okay, but
Okay.
if in other words, don't worry about getting exactly. If you got 99.7 here, it's correct. You follow what I'm
Yeah.
saying? It's correct.
Okay.
Okay, so don't worry about that. If this is what you got, like I said, it could be the program the way it's rounding up or rounding down. Okay, so don't worry about that. Yes.
Okay.
Somebody had a question? No? Okay, now what do we do with all this good information? Well, all our analysis is not complete. In other words, we don't have to go and do MF is equal to WFL squared over 8 and blah, 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 and blah, blah, blah. Everything is, we have all that information in this program, okay? So now, So like I said, this here are the reactions. And again, when we put in the right size beams, we're going to rerun the analysis and we're going to get even more accurate values here. But this is what I would use to design my columns. So these are all my CF values. In other words, all the factored compressive forces that the columns have to be designed for. Okay. So that's what I'm going to use this for. So when we go to columns, I don't have to calculate the CF. I will come to ADA, get my CF value, and design my column. That's what's nice about ADA. Okay. There's my CF values. Okay, and then of course, so in other words, in this case here, since this is very close, I would not design this column for this CF and that column for that CF. I would just take the highest one and make them all the same. Now remember, that's for the interior columns here. The exterior columns, well, when we get to exterior columns, it's quite different, but we will be using these values for the exterior columns. So that's for the column design. There's my CF values, the reactions. Now, these are my shears, okay? So in other words, here, I would like to annotate. Where's the annotate? Oh, here you go. Okay, so guys, remember, this is the shear force, okay? So in other words, this is going to be a continuous member from there to there. And therefore, this is going to be the maximum VF. So whatever you choose here, it's going to be a W610 by something. Well, then you're going to have to check the VR is greater than that VF value. This is your suspended beam, and therefore I look for the highest VF value. The highest VF value is this one. And then for the double cantilever, which goes from there to there, I look for the highest VS value, and that's when I will make sure that the VR is okay. And if I happen to use the same beam for here and here, then since I'm using it for here, I don't even have to check the VF for here. And of course, because this is going to be the same thing if I put the loads, the mirror image, and therefore it's going to be applicable for all these members here. So that's what's nice about ADA. It gives me my VF values. So the VF for the left cantilever is 329.9. See, I even dropped the 0.1, anti-gutsy, right? And then for the drop, for the suspended beam, I take the higher of the VF, and there it's 99.12. And for the double cantilever, I look for the highest value, and it's 291.4. So these are my VF values.
The drop-in girder, what is the 192? What is that?
The 192 is the VF. The 192, okay. The 192 is the VF on this side of the beam.
Oh, okay.
Okay. You see, because Rena, I can't go back to my ADA, okay?
No, I can see it now. It's just
You can
like
see it now. Okay, I'm glad you see it. But what you can do, I should have shown you this. I'm going to do this in ADA, but I won't be able. I'm going to have to close this, go to ADA, and I'll show you how I did it. But or I'm going to have to like split the screen and. Or maybe I can split the screen right now. I don't know if I can split this. No, I don't think I can split this, but can I split? No, I can't. You know, if I'm on presentation, I can't split it. But okay, so guys, there is. Okay, now these are my moments. Okay, now guys, very simple. Here's my drop-in beam, like this. Okay, it only has a positive moment. And of course, it's laterally supported at every 2 meters. So now I can go and size that because I have my LU of 2 meters of 2000 millimeters. I have my MF of 150.36, and I have my VF value. So I go into the tables and I pick a beam. And then after that, I will put an ADA, and then afterwards, I will check my deflection. So that's what you're going to have to do on your own. Okay. So for the drop-in, the MF is 156.4, okay? That's your MF value. And therefore, you know, okay, so I have a VF. So I isolated just the drop-in beam so you guys can see a little bit better, okay? I should have left this out because this is, I should have just picked this here. But there's my VF value, there's my FF value, and the spacing is the open web steel joist. So my LU is 2000. Now, of course, you go to the beam selection table, right? So I have, what is it, 157.4 0.44 and 2000. Now at this point here, I don't worry about IX because I will be putting the beam back into the, back into my model, into my ADA, and then I will run the analysis for deflection and see if it's okay. So you come here, and of course, like I said, for 2000, so you're somewhere in here, you're looking for, what was it? Whatever it is, you come down and you pick a beam, okay? So pick a beam and make sure your MR is greater than your MF, make sure the LU is less than 2000, you pick a beam, and that's what you're gonna have for your drop-in beam as your preliminary size for your drop-in, and then we'll check deflection. I'll show you how to do that. So everybody okay with that? You know what to do? Is everybody good with that?
Yes.
Okay. So that's how you design the, that's how you design the drop-in beam. And that's what's nice about ADA. Once you have that, you just go there, pick one, okay? Now, you pick one, you let me know what you picked, and I'll let you know if I pick the same one next week, okay? So now here, okay? Now what we'll do is we'll start by designing the left cantilever, okay? So the left cantilever, okay, this is the shear and these are the moments. So I will first design it for moment and then I'll worry about the shear, okay? Now, what happens here in the left cantilever, guys, what you have to realize is that what's nice about this is that, what does this tell you? This line here. Does anybody know what this line tells you? What happens at this point here? Or what happens at this point here?
There's no moment.
Pardon?
There is no
Okay, but what,
moment.
okay, so in other words, from here, there's no moment, okay? Now, what happens here? What do we mean that this is negative?
In compression?
Yeah, but what is in compression? Okay, here, what's in compression here?
The top surface.
Exactly, guys. In other words, when we say we have a positive moment, that means that the top flange is in compression, okay? And what happens here is that at this point here, the bottom flange goes into compression. And unfortunately, because our joists are only supporting the top flange, this becomes unsupported. And therefore, our LU becomes the full span. You see, and that's what people don't realize. So when you have this situation, because this is in compression, like in other words, here, the top flange is in tension and the bottom one's in compression. Here, the top flange is in compression and therefore here, the joists are supporting the top flange, but here, the one that's in compression is no longer supported. And therefore our LU becomes the whole span because of the negative moment here, okay? And that all of a sudden gives you an unbraced length of the whole span, which would be 10,000 millimeters. So that's number one. That's the first thing you should realize when you see these diagrams, okay? I no longer have a lot of support for elements that are in compression, therefore my LU. Now, you can shorten the LU, okay? You can shorten the LU and, okay? So MF is that, okay? LU is that, okay? Now, what you can do, okay, if you want, and we're gonna do this, okay? We can put knee braces, okay? We can put knee braces whereby we shorten the LU, okay? In other words, what we'll do is we will actually go and support the compression flange, okay? We'll put these knee braces, okay? And we will only be able to put them where our joists are. So what's gonna happen is that this is going to be our girder here, okay? Our joists are gonna be sitting on top here, like this, right? And then we'll be putting a knee brace so that we can laterally support the element that's in compression here, okay? And that's how you can reduce the LU. So I hope I didn't go over everybody's head, but in other words, as long as I'm holding the compression element of my beam, that I reduce the LU. If I don't go hold that compression part of that my beam, the LU becomes a whole beam, okay? In this case here. So we're gonna do that, or we're gonna see if we need to do that. Okay, so if you want, we can either have an LU of 10,000. In other words, don't go put those knee braces to go and hold, or what we can do, for example, look, what I like about ADA is that, and what I like about having 10 segments, okay? What I like about having 10 segments is that I know that this here is 10 meters. And I know that each segment here is 1 meter because it's 10 segments. So I come here 1, 2, 3. So here I know by where I have my other joists that I can put a lateral support, and I will be laterally supporting the negative region. So I know that I can go and support that beam, okay? And that's what's nice about ADA. It tells me where I need to put the knee brace and what my LU becomes. Okay, so here my LU becomes 4,000. Now, people say, well, why isn't it 6,000? Because here the top flange is supported by the compression is up on the top and therefore supported by the joist here. So I can either work on an LU of 10,000 or I can try to reduce it to 4,000 and see how that affects my beam, okay? So now, so what I did, okay, guys, I prepared a spreadsheet, okay? I prepared a spreadsheet and I hope you guys opened it, okay? And I will now open that spreadsheet. And this is what you need to do, okay? When your members are unbraced. In other words, if you want to calculate an unbraced length, I'm sorry you're taking so long. I'll have a sip of coffee in the meantime. Okay. Now, guys, I'm going to zoom in here. I apologize. I'm going to zoom in here. Where's view? I just want to go over this very quickly so that you guys, or do you guys have this open on your screen so I don't have to zoom in?
Yeah.
Sure.
Okay, so guys, so I won't zoom in because I want to leave it like, okay. So here guys, you know when you have, you know when the LU exceeds that maximum LU? Well, guess what? This is what you need to calculate the MR value. That's just step one. That's one of the equations that you need to calculate. It becomes pretty intense, right? Could you imagine having to do this every time? So here I told you what the ultimate moment capacity is. Omega 2 is a coefficient to account for increase in moment, okay, omega 2. And then L is the length of the unbraced segment. So in our case, L would be 10,000. We all know what E is, 200,000 MPa. IY, the moment of inertia about the y-axis now, no longer about the x, because it's the y-axis that's going to buckle out of plane, understand? IY. And then, oh, you've never seen this before. You also have a shear modulus for steel, which is 77,000 MPa. That's okay. Then Saint-Vivant's constant. That's for torsional constant. In other words, how the thing is going to twist. Okay. And then you also have a wrapping constant. I know you guys never got into this. So these are all section properties. And believe it or not, and here you go. This is how you calculate the value of omega 2. Omega 2, wow. I got to take the maximum factor moment in the unbraced length. Okay. Then I got to take the factor moment at 1/4 of the span, the factor moment at the mid span, and I got to take the factor moment at this 3/4 span. And that's how I calculate omega 2. Okay. Then on top of that, depending on the value of mu, depending on this value that I get from here, if it exceeds 2/3 of MP, and this is how you calculate MP, then I use this equation to calculate MR. If it's less than 2/3, then I use this equation to calculate MR. So I have to calculate this. I have to calculate the omega. First, I have to calculate my omega. Then I got to put it in here. Then I got to see that, calculate my MP value. This is the section, the plastic resistance of the thing. And after that, if I see that this value here is greater than 67% of that, I use this equation here. If it's less, I use that equation there. So that's how you do it. Okay. Now, what I've done for you is, of course, I prepared a spreadsheet here. Okay. Prepared a spreadsheet whereby this here, let me just get my mouse. Okay. These what I've done is I went to the first, I simply went to my load case number 1, my P1, okay? I clicked on the member. I copied MX in the spreadsheet off ADA, and I simply pasted them here. So that's how fast this was. So in other words, all I had to do was go paste the values from ADA here for my moment at 0, my moment at 1, my moment at 2, my moment at 3, 4, 5. Like these are the moments along the member of the member. Now here, I know that I have a linear relationship between at 2, like they want me to calculate the moment at 1/4 of the span, which is 2.5. So therefore I take the average of these two, and that gives me the value of MA. That gives me the value at the center of the span, which is this one here. And then at 3/4 of the span is the average of these two. So I let whatchamacallit, I'll let the Excel spreadsheet calculate the MA value, the MB value, the MC value. Then the spreadsheet takes these values, brings them up here, and calculates the value of omega 2. In other words, it just calculates that little value there, okay? Now, what I've highlighted in yellow is what you need to input if you want to use a spreadsheet. So for example, when I put in a W6M, I need to put the B, the T. All this does is it tells me, do I have a class 1 or class 2? And oh yeah, on top of that, this equation here is only good for a class 1 or class 2 section. So you got to make sure that you're in a class 1, class 2 section. So what I do here, by putting the B and the H and the T and the W, this tells me if I have a class 1 or a class 2. And if it says no, I have a logical argument here that says no good. Therefore, I'm not even supposed to be using this equation, number 1. So that's the first thing I check. Then after that, I use the section properties to calculate the value of MU. So this is the value of MU here, okay? And then on top of that, I go ahead and look at, for example, it compares the value, it compares the value of MU compared to the value of MP here, okay? And depending on these two, it calculates the value of MR, okay? So right here, what this thing is telling me is that if I happen to be using a W610 by 82, what is the spreadsheet telling me? This section is no good because my MR value is less than my MF. Everybody sees what I'm doing? Now, this is for that for the part that's between, and then this is just for the cantilever part. Okay, now for the cantilever part, this is another equation that you need to calculate the value of what they call MC. Okay, MRC. Okay, this is just for the cantilever part, and that's okay, and therefore, and here, well, this, I'm sorry. Okay, so here all of a sudden, okay, I have a value of, of MF at the cantilever, and also here, it's no good. So therefore, if I want to use a W610 by 82, and these are all the section properties of a W610 by 82, and then what I've done in the spreadsheet is that for trial number 2, okay, if you notice here, okay, I don't have any more yellow. In other words, whatever I put here will get transferred to my next trial for my load number 2. The only thing I have to do here is I have to, on ADA, I have to click on P2, pattern number 2, click on the member, copy the moments on that member, and then paste them here. And then after that, this I have to do for everyone, the tip load, and this is my shear, and that's the value, okay? And all of a sudden, I look at case 2, it's no good. As soon as I get a no good, no good, no good, guess what? I cannot use a W610 by 82. So guys, I'm giving you the spreadsheet so that if ever in the future you need to calculate something that's got an overhang, it's got a negative moment and a positive moment, take the spreadsheet and do your design with the spreadsheet. Now, let me show you what happens. Let me go back to case 1, okay? Now, remember I told you that if we put a knee brace and go and laterally support the beam at 4 meters, let me put 4 meters here. So all I gotta do now here is change 4 meters, put 4 meters, and look at this. Now, all of a sudden, guess what? I'm okay. I'm okay. So by laterally supporting the thing, I can get away with a W610 by 82. Now I'm okay. And of course, okay, and now it's okay for case number 2. Now let me go, case number one, guess what? It's okay for this side, but it's not good for that side, for the cantilever side. So I can't use it. Then I go check, as long as I get one, it says no good, then I've got a problem, okay? Then if I go to load case number 3, it's the same thing here. It's okay for the one in the middle, but it's no good for the cantilever side, okay? And therefore, as soon as I get one no good, I can't use this section anymore. The same thing here. It's good for the part that's in there, but it's no good for the oh, it's good for both of them here. Great. So in other words, for load case 1, load case 4, it would be appropriate, but all of a sudden for load case number 2 and load case number 3, guess what? It doesn't work, okay? So now what I want you guys to do, just for the hell of it, okay? I like you to take the spreadsheet, okay? Replace this with a W. I want you to replace this with a W610 by 92, okay? Replace that with a W610 by 92. Now, on every spreadsheet, it's gonna get changed here, but then I want you to go put in all the values here for a W610 by 92. Leave this at 10,000, okay? Leave that at 10,000 and see what your results are. And then if you see no good, change that to 4,000 and see if it's okay. And see if you can get away with the W610. If the W610 by 92 is no good, then go to the next one. You go to W610 by 101, okay? And try that one. So that I expect you to do it on your own. Okay, so you've got this spreadsheet, and like I said, I made it, and then here, these don't change because the analysis stays the same. The only thing that's going to change is the resistance. So you don't have to bother changing any of these values, okay? So, so this you don't change, you just go change. Oh, sorry. And don't forget, guys, I apologize. If you're going to do this, do it on the first spreadsheet because the first spreadsheet transfers all the information that you need to the other spreadsheets where it's the same information. So make sure you do it on the first spreadsheet. Put a W. I did it wrong here. I should have done it here. I should have put a W610 by 92. Okay. And then it would have changed it on all the other spreadsheets. And like I said, and that's why I sent you that third file where you have the W shapes. That's where you'll find the information with regards to the B, the T, the H. The H is simply equal to D minus 2T is your H value, W, and then you'll get your IY, your ZX, you'll get your J, you'll get your CW, all from that file that I sent you that's under labs. Yes.
Sir?
Yes.
Sorry. You said the H is D minus T?
No. When you go to the table, you're going to see one value in the table that says D minus 2T.
Oh, okay.
Which is, and that's what H is. In other words, you take the total depth minus the top flange and the bottom flange. That gives you the height of the web. You understand? And that value is already calculated for you in the table. So you don't even have to calculate that. Okay. So, okay. So I'm going to leave you that. So you take this one here, like I said, on the very first load case, modify only the values that are in yellow here. Okay. And then you'll see that they're all going to get modified everywhere else. Okay. And here, don't forget, you're going to have to go and modify this value here, the D here. Okay. These top and bottom loads, don't change them because they're going to be the same. Anton, you have a question? Anton, are you there?
Sorry, sir.
Yeah,
So,
go ahead.
So basically on the second page, where it says trial section W610 by 92.
No, on the first page, I made a mistake. You go to first page, you put a W610 by 92, and you put all the properties here for W610 by 92.
Question is that a CU or a CW next to the J?
This is a CW.
Okay, so what's where would I get this value? Did I calculate this or?
No, I told you, you take that W shape table.
Okay.
And all the values of all the geometry and all the section properties. Okay, hold on. I'm going to stop sharing this. I'm going to open one up so you guys can see this. Okay, hold on a second. So in other words, guys, I'm going to close this. I don't save. I don't want to save it. Okay, I'm going to escape from here. And I'm going to go and look for, I'm going to have to go and open one up because I have to go and open up Okay, let me go and find one. Okay, I'm gonna have to go and find one so I can open one up here, W shapes. Now I sent you this. Okay, let me just, okay. Let me go back. Okay, I've got to go to my, sorry guys. When I ask you to open up files for the lab, open up the files. And that's why Antonio asked a question, because if you would open up the files, you would have seen it in the table, okay? But I'm gonna do this once, and this way we're all on the same page, not a problem. So where is, okay. So did you open up this table, Anton?
Yes, yes, sir. I just did.
Okay, so here, I'm gonna minimize this so everybody can see it. So Anton, okay? What I sent you here is all the section properties and all the geometric properties of every W shape that is produced.
Okay, all right, okay, I understand.
Okay,
All right.
so unfortunately, in my handbook, Anton, this is one side of the book, and the next sheet is the other side, and I couldn't put them side by side. It wouldn't have been legible. You follow?
All right.
So, in other words, this page here is right beside this page here.
Okay.
Okay, you understand what I'm saying?
Yes, sir.
Okay, and if you want to make sure you're on the same profile, if you see here 343 kilograms per meter here, right? You'll see the same value here. So you know you're talking about the same one here. And then this is the imperial designation for
okay,
that one. In other words, it says 44 inches by 230 pounds per foot.
Mm-hmm.
Okay, so now if I go down, I'm going to go down to a W. We might as well, you guys, I hope you have Excel spreadsheet open up now so you can put the values in right now. Okay, so here is a W610 by 92 right here, right? Now I need to know the ZX value. So I go down, the ZX value is 2,510. There's my ZX value. And that's what I would put in that cell on the load case number 1 for ZX. And don't worry about 10 to the minus 3. That's already built into the equation, okay? Then my IY value, that's 10 to the minus 6. That's already there. It's 14.2. So put 14.2. Right now, what you should be seeing on your spreadsheet is 12.1. Am I correct?
Yeah, you are, sir.
Exactly. In other words,
Yeah.
okay, so these are all the values for 82, but I'm going to change that to 92 now, okay? So I'm going to have 12.1. And then I need the J value, the torsional constant. That's 710 instead of 488. And then I'm going to change the wrapping constant from 1040 to 1220. So there I've put in all my section properties. Then I go to the next page, and this is where I get the value of D. You got to go change the value of D. Well, in this case, it's the same as, well, the other one was, did I have? Well, I made a mistake because it should have been 533. I put 603. So D should be 603. I made a mistake when I put in the value. Okay. And then B is 179. T is 15. W is 10.9. And Omar, this is your H, D minus 2T. In other words, the total height minus, and that gives you the H, the height of the flange, 537 there.
Sir, quick question.
Yes.
I'm not trying to be smart here, but when I check the ADA, you can check the property of the member, right?
Okay.
So when I compared these numbers, the one you gave us and the one on ADA, they're not the same. On the W610 multiplied by 125.
W610 by, you have to go down to 80, you got to go down to 94.
94, yeah, sorry, wrong place. Yeah, cool.
If you go to 94, like I could have just told you, go to ADA, right? In other words, I'm going to open up ADA, right? If you go to ADA.
Actually, they're the same. I'm sorry, I just checked.
Exactly.
Yeah.
In other words, you can get that information either from ADA, right? And if you don't happen to have ADA for whatever reason, I gave you the whole table. Okay, so you can get all those properties from ADA. Yes, Omar. Understand?
Yeah, thank you.
And if ADA doesn't have the same values, I wouldn't trust the program.
Okay.
Do you follow what I'm saying? You know what they did? One guy sat there and created a whole database of the program. Okay. Okay. So guys, try it and try it once with an L equal to 10,000. See what happens with a W610 by 94. And then if you see that it's no good for whatever reason, put 4,000. And if it happens to be good, then you know what size that girder is going to be. Okay. So that's now. So that's what I did for, so that's how I simplified your life. You simply have to go and modify slightly. Okay, let me go back to this here. Okay. Okay, so there's, like guys, I'm just gonna go through this and don't worry, I'm not going to just call it a day. If any, I'm gonna stay on to answer any questions. How are we doing time-wise? Oh, we got time, we got time. Okay, so guys, you guys can do that, and I'll be around. And if you have any questions, we'll share the screen, and I'll help you through it. So all I'm saying is that right now, I gave you this file. I showed you what you can do with it. Okay, and if you're curious to know, I'll show you even how easy it is to cut and paste, values from ADA into that spreadsheet. If you guys don't feel comfortable to do that. Now, that was just for the left cantilever one. Now I'm going to have to do the same thing for the double cantilever. And the reason why I have to do it for the double cantilever is because with the double cantilever, the MF values are completely different from the left cantilever. And then of course I have to check that one. So what I did the first time around is now in this case here are the values for the double cantilever. Okay, so it's the same thing. It's almost as if it's got one cantilever. So this is the backspan here and everything else. Okay. And of course, there's my VF value, there's my MF value, okay, the biggest MF value that I have. And again, the LU is 10,000, and that's because of that famous, okay, like I said, because, okay, where am I? How come I can't draw? Not allowing me to draw anymore. Could you believe I can't use the annotate anymore? Wow, I love this program. Yeah, I can't even draw anymore on the screen. Okay, so anyways, I was hoping to show you that, like I said, because here the excuse me, the bottom flange goes in tension here, and therefore we have it goes from tension to, and this is the point of inflection. We have the same thing, and we're not laterally supporting the bottom flange, therefore the LU becomes the whole length of the beam. Okay, and then like I said, we can go back to here and we can put a knee brace, 1, 2, 3. So therefore at 4 meters, we can laterally support the bottom one, 1, 2, 3. So here we have to do it on both sides, once there and once there. And therefore we can bring down our LU to 4,000 if we want to put that in. And of course here. Now what I've done here, okay.
Excuse me, sir.
Yes.
Sorry to interrupt, but I don't know if you're showing us something else right now, but you're stuck on, or what I see is just the W-shaped 690.
Yeah, the PDF.
Yeah.
Okay, I apologize. Okay, because I forgot to stop sharing that file. Okay, so let me go back to, sorry. Okay, sorry. Okay, so I apologize. Thank you, Thomas, because like I'm all over the map here. Okay, but let me go back. Okay, stop. Okay, so do you see the PowerPoint now?
Yes, I do.
Okay, so I apologize for that, because I instead of going back to my main screen, I went just to the file, and unfortunately that's why I picked the wrong screen, you understand? So I apologize for that. Anyways, so now do you guys see that we're back to the, I'll go over this again. Thank you, Thomas, for jumping in. Okay, so now we did that for the left cantilever. We're going to do exactly the same thing for the right, for the double cantilever. Okay, and of course these are the values that I got from ADA. And again, like I said, this is for that knee brace to show you that you can go laterally support the compression flange here. And okay, and therefore I sent you this file also, okay? Now, here, it's exactly the same thing. In other words, the equations don't change. Everything stays the same. Like I said, how did I do this? Well, I basically, okay, if you, for some reason I can't, I'm going to show you this after, like once I close my PowerPoint, but I simply, so here what I did was I decided to try a W610 by 101. I put a length of, the length of the span here. I put in all the section properties, okay, for the all of one, and look what happens, okay? So at a 10 meter, okay, the 101 is good for case number one. I'm sorry, I should have started with case number one. Okay, it seems to be okay for case number one. It seems to be okay for case number two. And that's without putting any knee braces. It's okay for case number three. And it's okay for case number four. So that means that if I happen to use a W610 by 101, okay, and I do not put any knee braces, okay, then I can satisfy all the conditions. And if you look, guys, it starts getting very close to the actual. So like there's, like it's optimized in terms of it. Now, what I'd like you guys to do for this one, okay, you don't have to change the loads. Go back to case number one, okay. What I'd like you to do is put here what you did for the, the left cantilever, put a W610 by 92, change this length from, like, leave this at 1,000, and if it doesn't work, change this to 4,000 and see if it works. If it works, it's preferable to have the same beam going right across, like for the left cantilever, for the double cantilever, and see if you get the results for a W610 by 92 here. Just change this to a W610 by 92 and see if it works for 10 meters. And if it doesn't work for 10 meters, try it for 4 meters. If it works for 4 meters, well, then that's what we're going to use. We're going to use a W610 by 92, even for the double cantilever. And I think you guys should be able to do that. Okay.
Sir,
Yes.
do we have to make them on a separate, like, do you want to see at the end, do you want to see the Excel sheet, or we say what works at the end, like when we submit our things? Do you want to see the Excel sheet?
I don't want to see this sheet here. Okay. I don't want to
Okay.
see this sheet here, but I want to see this sheet here, and I want to see this sheet here.
Okay.
You follow?
Yeah.
Because I'll be checking, for example, if you guys modify this, if you're using it properly. You understand? You don't have to change this. Okay. And so this is what I expect to see. In other words, once you change this, I expect to see a copy, like a copy of this sheet and a copy of that sheet. Yes.
All right.
You follow?
Yeah.
Okay, so that's going to be for the double cantilever. Okay, and then after that, once you've satisfied yourself that a W610 by 92 is okay, then I want you to check for the shear. Okay, in other words, this is the maximum shear, and of course, if it's good for this one, it'll be okay for this one also. And check for the shear for your check for the shear W. That's anyways. And of course, always take 80% of the VR, because eventually you're going to have to make holes to support like this beam here and so on and so on. And then at the end, okay, what you're going to do is you're going to replace your members with what you've designed them to be, and you'll have to check for deflection. And next week, I'll show you how to do that. Okay. And that's what you're actually doing. You're going to be checking the deflection. Like this is deflection under P1, this is the deflection on the P2, this is the deflection on the P3, this is the deflection on the P4, and then you just check, you decide what is the maximum deflection that you want, if you want it to be L over 240 or L over 360, and you just check to make sure that none of these deflection exceed your deflection criteria, and you've checked all your deflection with ADA. And I think that's it. So guys, I'm going to stop sharing.
Sir.
Yes, hold on. I'm going to, yes, go ahead, Adriano. Like, look, we have a whole 40 minutes or 35 minutes. I'm here to help you guys. We'll share your screen. I'm here to help you out and so on. So yes, go ahead, Adriano.
No, I just want to ask you, in the Excel sheet,
Yes.
the positions from 0 to 10 meters.
Sorry,
That,
the length.
yeah. So I just wanted to make sure that represents only the first section, right?
That represents the length, that's the unbraced length of the span that you're trying to design for.
Okay. And the bending MX is when we click on the beam, let's say on ADA, and get the properties and the bending on each
Okay.
meter.
What I'm going to do now, okay, let me just do something here, okay? I'll tell you, okay, so let me close this, okay? And let me open up ADA. Do you see my ADA on the screen?
Yeah.
Okay,
Yeah, I see it.
so I'm going to minimize that. Don't look at these ladies. Those are the other two ladies in my life. Okay, and then I'm going to open up one of the Excel spreadsheets, okay? So now I've opened up, which one do I have opened up here? The W610 by, okay? So, okay, oh, sorry. Do you see both the spreadsheet and the ADA?
Yes, sir.
Yes.
Okay,
Yes.
okay, so what I'm saying here is that, like, in other words, I'm not sure. Okay, first I hate, because everything pops up here, guys. Okay, I'm on the load case number 1. Okay, I just want to make sure that, well, what I should do is I should shrink this so I can go ahead and see my load cases. Okay, so here you go. So this is what I do, okay? I have my spreadsheet open like this. Sorry guys, please
But
bear with me.
you can
Okay.
take the window and drag it to the left, all the way to the left. It will like be half-half.
Take
Both
the
windows.
Okay, well, you mean take the window and drag it to the left?
Yeah,
Yeah,
take the
just hold it
Excel.
from the top.
Pull it from the top here.
Yeah.
Like hold it, go to the left. No.
Hold it at the top and go to the left.
Yes.
You mean go here?
No, like even more. It should like see like an effect, like a flash or something.
Oh, anyways, look, I'll play with it one day. But what's important here is that Omar is requesting remote approved. Here you go.
Let's see. Okay. I can. I don't think if I. No, I can. I can. Oh wait, yeah. Okay, that's gonna be like this a little bit, like this, and then you choose this. Oh, sorry. Here we go.
Oh, you mean, okay, where the X gives you exactly half, is that it?
Yes.
Yeah, exactly. That's it.
Okay, thank you for that. But sometimes I want to see more of one thing than the other, but that's okay, not a problem. Okay, so this here is my W610 by, okay, my double cantilever. This was my load case number 1, right? So what I did is very simple. So I make sure that I'm on load case number 1 here. Fair enough. And this is the member that I'm looking at. Fair enough. So all I do is I double click on it, and then I come here, I take this, I say copy, then I come here, click here, and I say paste. And that's how I paste the results on my spreadsheet.
Okay. I was just on the wrong member. That's why I wasn't getting the same values.
No, okay, but you understand, Adriano?
Yeah. Yeah.
So in other words, what I did for the first one I showed you, right? And close this. Okay, so what I did for the first one, like this one here, okay, so I went here, I make sure I'm on that member there. If I'm doing the first load case on my spreadsheet, I won't do it here because I closed the other one, I think, okay? I do the same thing. In other words, I double click on the member, it gives me the MX value here, okay? And then I put it on my spreadsheet. Then I go, and then I change, so that's how fast it is, you understand? So, and then I close this, I'm on my second load case here, so then I change this to number 2, you know? Everybody understands what I do?
Yeah.
Double click on this, and I love working with the spreadsheets because the spreadsheet gives me the moments, it gives me the distances where they cross, it gives me the shear, you understand? It gives me the displacements. I love working with the spreadsheet. So, and therefore I simply copy and paste, okay? And that's what's nice. Sorry?
Sorry to interrupt, but for each load case, we have to check every member, right?
Well, I mean, like each load case is only for one member.
Oh, okay.
Do you follow what I'm saying? Like, in other words, right now I have 4 load cases and I'm trying a W610 by 101. But that one member has to be good for each load case. If there's one that's no good, I can't use it. And that's why we do different load cases. Understand? If you remember when we were doing the W610 by 82, it was okay for the first one, but not okay for the second one. Not okay for the third, okay for the fourth one. So I still can't use it because it's not good for all of them. It has to be good for every one of them. And that's what I'm telling you, like for the double cantilever, you don't have to change these. These values stay the same in your spreadsheet. All you got to do is go change the section, trial section, and put the properties up here. And once you do that, Excel will do the rest for you.
But like, let's say in this case, sir, like on your ADA, you chose the first section, right?
On the ADA, like when you're saying I chose the first section.
Like
member,
the first member.
No, don't say first member. This is the left cantilever. Refer to this as a left cantilever. In other words, when I'm looking at it, it's the cantilever that's on the left of my diagram. And this here is a double cantilever. So when you're saying
what if you were to take the double cantilever and put it in the Excel sheet?
I did. And that's what this one is. That's this one here is for the double cantilever. If you look here, I say that this is for the double cantilever girder.
Oh, okay.
You understand?
Okay, okay.
So that's how I know I'm using the right spreadsheet, because this is for my double cantilever.
Okay, that makes sense now.
Okay. Now, this is me. I have to remember what I'm doing. I mean, you know, like, it's not like Excel tells me, oh, you're using the wrong spreadsheet. I have to make sure I'm using the right spreadsheet. You understand?
Yeah, no, it's clear now. Thank you. Okay.
And what the spreadsheet does, Adriano, just so that you understand, what the spreadsheet does is that it checks the moment in here. Okay, just so you can understand what's happening. Okay, let me just, now you understand why I couldn't annotate before, because I wasn't sharing my screen. I apologize. Thanks, Thomas, for letting me know. So what this spreadsheet tells me, and you can't see it here, but what it does is that it tells me if the moment here is okay, and it tells me if the moment here is okay because of the cantilever. Okay. And that's what this second half does. It calculates the resistance of this section of the beam right in here. This one checks this one, and this one checks this one. That's what these two sheets do. And then here, this one checks this one, the first sheet, and the second sheet checks the cantilever.
Yeah, it makes sense. Now I understand it perfectly.
Now, do you understand how it works? Okay.
Yeah, yeah.
And guys, look, so just to jog your memory a bit, okay? Where I have my pin, the pin means that there's no resistance in rotation. All the moments are zero. So that's that's all your pin connections right there. All the moments are zero. And that's where it goes from from positive to negative, from negative to positive. I mean, like here. So all the moments are zero. So here it's because of the pin, and here it's because of the point of inflection. Okay. And guys, like I prepared this for you because could you imagine if I expect you to do this on your own? Understand? So I think the spreadsheet will. Okay, so I'm gonna. Okay, so I'm gonna. Okay, stop sharing. Okay, so guys, go ahead, do what I asked you to do. Okay, and I'm here to answer any questions. I think I put. I can share your screen. Okay. And let me know. I'm going to stop the recording because this way, if you guys pause, I'm just going to pause. Resume the recording. I'm going to go back to my whiteboard. Okay. Jan, you're the one that asked me the question, but I'm addressing everybody. Okay.
Okay.
This is my beam. Now I'm just going to draw the left cantilever for now. Do you understand? Now this is going to be eventually your column and all that. Okay, so this is my beam. I haven't drawn it to scale, but you can appreciate what I'm doing. Okay. Now, if you look at the moment diagram, okay, all the moment diagrams do this. They go like this, right over the column, they go up, and then they go to zero. We agree?
Yeah.
Do you understand?
Yeah.
You see that? Okay. So this is the moment diagram. Okay. Now for every load case that we have, they basically have the same pattern, not the same value, but the same pattern. Do you follow that?
Mm-hmm.
Okay. Now this represents a positive moment, this represents a negative moment. Now, there's no such thing as positive moments and negative moments. All this means is that positive means bottom is in tension, top is in compression. That's what positive and negative means. So here, what is this? What happens to this side of the beam? Where's the compression?
Bottom.
To the bottom.
Okay, so here's my compression. Here's my tension. Same beam, is just that at that point of inflection, it switches. Everybody follows? Now, where are my open web steel joists? They're sitting right here on top. You see that? You understand? That's where my open web steel joist is. There's another one here. Okay, so which flange is the open web steel joist laterally supporting? It's only supporting the top one. I don't know if you guys can see that or you don't see that. In other words, it's only the top flange of my beam that is being laterally supported by my open web steel joist. Do you follow?
Yeah.
Or it's not clear? Now, guys, let me just put it another way to you, okay? Everything that we've done in class, I want everybody to listen to this, okay? Everybody that was in class, okay? This was our beam. Our beam was simply supported. You understand? Our beam was simply supported, and therefore the tension was all at the bottom. You understand? And therefore we, okay, and therefore we didn't have to worry about. And as long as the top flange was lightly supported, the compression side, that was our LU. Okay. Now here, because these open web steel joists are only supporting the top flange, I should have changed the color. Okay. What? Oh, I should bring that back. Sorry about that. Because it's only supporting the top flange, and now I screwed up my drawing, sorry, okay? What happens here is when this flange goes into compression, there's nothing to hold it from buckling, okay? And therefore, if I do a cross section here, okay? I draw a cross section here. Here is my beam. Here is my beam. I'm doing a cross section. Here's my column underneath. And here's the open web steel joist sitting on top. Does everybody understand what I'm drawing?
Yeah, we see what you're drawing, sir.
Okay, okay. So which flange is the open web steel joist laterally supporting? Is the bottom one being supported anywhere?
No.
Okay, so it's not being supported. Therefore, since at the column this is in compression, the LU becomes the whole length of the span. Okay, so if I want to support this, I need to put in a knee brace. So in other words, I will take a piece, whatever, and I will come and attach here, and I will attach it to the truss here, and then all of a sudden I will come and laterally support the bottom flange where it is no longer where it goes back to being positive. And this happens to be, according to ADA, this happens to be at 4 meters away. If I go back to ADA and if I look at the point of inflection, the furthest point of inflection is not more than 4 meters away. So if I take my joist here, I can use that joist and I can create that knee brace to laterally support the bottom flange, and therefore my LU now becomes only 4 meters. And that's why you can reduce the LU. Instead of it being 10 meters, you can reduce it down to 4 meters, because you will be specifying your drawing to add a knee brace at that joist. So on your drawing, okay, on your drawing, you're going to have your drawing here. You're going to show all your members. You're going to have your column here. And then you're going to be showing your open web steel joist. You're going to show your open web steel joist. You're going to show your open web steel joist. You're going to have 5 of them, 2, 4, 6. I'm missing one. Okay, I should draw this properly. Clear all drawing. So here, this is going to be, so here's my column. Okay, here's my column, here's my Gerber girder, here's a cantilever of whatever it is. Okay, so here's my open web steel joist. You're going to show your open web steel joist here. And on your drawing, what you're going to do is you're going to, at this point here, you're going to put a little asterisk here. You're going to put a little asterisk, not here, sorry, I'm drawing the wrong one. Erase. Okay. Okay, so on your drawing, you know that you're going to come here and you're going to just show a little asterisk here, okay? And then in your legend, you're going to say, you're going to show a little asterisk there, and you're going to put, and you're going to write knee brace. And by putting knee brace, the manufacturer of the joist knows that when he designs his joist like this, what he's going to do, he's going to provide a member so that it will come and loudly support the girder that is supporting the joist. And by putting a knee brace there, I'm going to be loudly supporting the compression part of that flange that has a negative moment. Is that a little clearer? Because guys, yeah, the concept here is that you have to keep in mind, okay, is which element, like if you don't understand, like if you don't understand that when I look at these bending moments, okay, if you don't understand what these bending moments are telling me, they're just telling me on which side is the tension, okay, then of course this is all, it's incomprehensible. So if you don't understand, like that's what these bending moments are telling you. In other words, they're telling you, where's the tension? The tension is on this side. The tension is on that side. And of course, when it comes to reinforced concrete, it's very important because you want to know on which side you should be putting the steel. So you always put the steel in. So for reinforced concrete, it's very important to know which side is the tension side. And for steel, it's as important because you want to know which flange is going to be on the tension side and which flange is going to be on the compression side. So you can take a look at whether that flange is lightly supported or not. And in this case here, because the open web steel, because the open web steel joists are only supporting the top flange, the bottom flange has an LU of the length of the span. In this case, it has an LU of 1,000 meters. And therefore you have to design it to see if for that LU is the MR greater than or equal to the MF values that you got from your analysis. And that's what the Excel spreadsheet does for you. By putting in just the values of the properties of the member you want to design for, the spreadsheet is going to tell you yay or nay. In other words, it's going to tell you, is the MR greater than the MF? And in other words, that spreadsheet would be like buying a program to design cantilever beams. You understand? Instead of buying one, I just developed it myself. That's all it is. Okay, so stop sharing. Does anybody have any more questions? Now's the time, guys.